Welcome back. In the previous lecture, we have seen about series RL circuits. In this video, we will say about series RC circuits. These RC circuits are used widely. You can see them in your day-to-day life. So many places you can see these series RC circuits. In your radios, in your traffic lights. See, the traffic lights also is a part of your RC circuit. With the help of your simple RC elements, by varying them, you can adjust the timings at the traffic lights. Even in our body, if you carefully see your artificial heart pacemaker, what we call it as, right? So it is also based upon your RC circuit only. So RC circuits are widely used nowadays by electronics and electrical engineers. And today we will see what happens when a single phase AC supply is given to a series RC circuit. So let me start with a picture of RC circuits. See, this is a simple picture of RC circuits where this is a single phase AC sinusoidal signal which is provided to a resistor which is connected in series with a capacitor. Okay. Now both of these offer resistance to the currents. It directly opposes the flow of current, whereas it opposes any change in potential drops across it. And the impedance which is offered by this element is given by R itself, whereas this one it is given by minus J XC, where XC is given by 1 by omega C. This is we have seen in the last class. Now, what is the total impedance which is offered by this series RC circuits? So the total impedance which is offered by series RC circuit, as already mentioned, it has resistance and capacitance. Resistance impedance is given by R, whereas capacitance impedance is given by minus J XC. So the total impedance now, see, this is R, first element, this is C, right? So its impedance is R, its impedance is minus X. So both are in series. So Z is equal to Z1 plus Z2. So I'll take it as R plus of minus AX. This is my total impedance. If I substitute a value of XC is equal to 1 by omega C, right? So this will come to this point. This is the impedance in rectangular format or complex variable format. Now, if you want in polar form, what you should do? This is the representation in polar form. Actually, earlier it was in rectangular form, right? Now, if you want to convert it into polar form, the magnitude is given by square root of R square plus XC whole square, whereas the angle is given by tan inverse of the imaginary component. Imaginary component is minus XC here. Minus XC by R. Minus XC by R. Okay. Right. Minus XC by R. Tan inverse of minus 1 by omega C R. So when I do this one, the current in the circuits is generally given by, see, V is equal to Vm. That's an angle of 0, because defaultly we take voltage angle as 0 unless if it is mentioned. The impedance now, if I represent it in the polar form, this is the representation, right? This is generalized representation, Vm sin omega t. This is R plus 1 by j omega c, right? Now, the magnitude and the phase angle, now V by Z is my current, right? So if I divide this one, so this is my magnitude Vm by Z, this is the magnitude. Angle 0 minus of minus pi, 0 minus of minus pi, so I'll be getting, sorry, this is plus, okay, 0 minus of, yes, sorry, I have written it only minus here, so okay, this remains the same, 0 minus pi. So this is my angle. Now My current is Vm magnitude by R square plus Xc whole square tan inverse minus phi, right? And what is phi in my case? It is minus tan inverse of 1 by omega c, because it was minus was here, so tan inverse of minus theta is minus tan inverse theta. So I have got it outside. Okay, don't worry about that. This we have seen in the previous slide. This one. Now, how to obtain the power factor? As already said, power factor is given by the cosine of phase angle between voltage and current signals, right? So my voltage signal was very simple. It was Vm at an angle of 0. And this is my current, which I can call it as Im if you want. And this is my angle, current angle. So what I should do? Cos of 0 minus of tan inverse of minus phi, right? So in this present case, voltage and current, they have the phase angles of 0 and minus phi, right? So this is angle minus phi. So 0 minus of minus phi, I'll be getting phi. So this is my angle. So cos of phi, where phi is minus tan inverse 1 by omega c, right? So if I substitute this, I'll be getting the value of this. Okay. So in this case, if you carefully observe, my series RC set is the phasor representation. Now, this is the representation of a voltage and current signal. Now, if you carefully see, this is 0, this is 90, this is 180, this is 270, and this is 360. This is the approximate representation. This is your voltage signal. Okay. See the current signal. The blue color one is a current signal. See, current signal is starting somewhere ahead of my voltage signal, which means that the current is leading the voltage by some angle, which may not be greater than 90, but not less than 0. Okay. So, in series RC circuits, current leads the voltage by an angle 0 to 90 plus. Okay, so that's fine. The power factor is considered to be leading because the current is leading. In series RC circuits, the power factor is considered as leading. Try to remember this one. Okay. Now, this is the phasor representation, right? See, this is my representation, right? So what is VR? VR is nothing but I into R. Whereas VC is I minus J by XC. Right. So if I take current as a phasor, right, this is IR voltage. It is in the same direction. Whereas here it is minus J, which is nothing but minus 90. So this is VR, this is my VC. Right. So when this is VC, so I should start from here, right? So this is VC. So the summation of these two is my Vs. Now see here, what is the final representation? This is I, this is Vs. See which is leading? Current is leading. Okay, so that's why the power factor is considered to be leading in case of RC circuits. Okay. Now the impedance triangle. So this is R, this is XC, and this is Z. Okay, whereas Z is equal to square root of R square plus XL whole square. Okay, so with this, I think I'll be closing this RC circuit. In the next video, we will see what happens when R, L, C are combined. Okay.